what is Coolbrook doing and why is it important?
Coolbrook are trying to decarbonise heavy industry, and it's the high temperature, high thermal power stuff that at the moment there's very little you can do other than burning stuff. It's really hard to do anything else, but we've got the magic answer that solves that.
We have come to a pretty controversial location to talk about a massive problem. How do you electrify stuff that needs temperatures hotter than a volcano? Because let's face it, when it comes to cement and steel, heat pumps, they're not going to cut it. So we've come to visit a company called Coolbrook, who have developed RotoDynamic technology, borrowing ideas from aerodynamics, my favourite, turbo machines, and rocket science, right here on Earth. I am extremely excited, and if you are too, we'd love it if you could like and subscribe. And welcome to the Everything Electric Tech Show. Our 3 free YouTube channels on EVs and clean energy tech are funded by our fun-packed test drive-tastic events in the North, West and Greater London, and our events down under. Next up, Everything Electric North 2026. Plus, check out everythingelectric.store for merch and much more. Back to the episode. Now, before we show you exactly what Coolbrook's magic answer is, it's important to understand the enormity of the challenge they're trying to solve. Hard-to-abate sectors are hard to abate because of literally physics, really. Cement, steel, aluminium, chemicals, petrochemicals all need temperatures in excess of 1,000 degrees C. And the cheapest and easiest way to achieve that heat is often by burning coal or gas. Now, the issue with that is that these industries are both essential, but contribute about 25% of the global emissions, more than 5 times the emissions of shipping and aviation combined. It is absolutely huge. So what are the alternatives? Heat pumps. In theory, but you'd need multiple stages just to reach those temperatures, making it complex and impractical. Electric resistance heating. Sounds simple, but most materials fail long before 1,000 degrees. You'd basically have a single-use heater. Green hydrogen works, yes, but it's inefficient. You lose energy making it, transporting it, and then burning it. End to end, it can use around twice the electricity compared to direct electrification. Carbon capture is possible, but expensive, inefficient, hard to retrofit, and usually subsidy dependent. And lastly, biomass. There just isn't enough of it, maybe 10 to 15% of demand at best. So, if none of these scale easily, where does that leave us? Well, the answer lies in technology first developed in 1884 by Sir Charles Parsons, who invented the modern-day steam turbine, unlocking efficient electricity generation. Those same principles went on to power the jet age, enabling aviation. And it's those principles that Coolbrook will leverage to electrify hard-to-abate sectors like steel, cement, aluminium, chemicals, and petrochemicals. Which is what brings us to this controversial location where their pilot line facility is proving the capability of this technology to crack Naphtha. We are at a petrochemical plant, something I thought I'd never say on the Everything Electric show.
This is a research campus where a lot of research is taking place in chemicals and materials. And it's actually part of the chemical side where there is a big petrochemical production, which indeed exists for over decades.
And also, it used to be, from what I understand, a coal plant, and it's kind of gone through various iterations. Sort of makes sense that it's paving the way for the clean energy transition.
Absolutely. We have done a couple of transitions from this area, and now we're looking at the new energy transition, and this is a great place to facilitate that and to bring the technology to the next level.
The petrochemical site in question is Chemelot in South Limburg, and we're just next door on the Brightlands Chemelot Campus, an open innovation hub where scientists and startups are moving chemistry beyond fossil fuels and towards circular and bio-based materials. Which is why Coolbrook is here to test its pioneering RotoDynamic Reactor. They are testing it on one of the most energy-hungry processes in the chemical industry, steam cracking. Traditionally, this relies on gas-fired furnaces to heat naphtha until it breaks apart. And Coolbrook does the same job using pure electricity, heating the material to around 1,000 degrees Celsius in milliseconds. That heat cracks molecules into ethylene and propylene, the building blocks of plastics. By electrifying the process, Coolbrook removes combustion emissions and increases yields with more precise heating. Ultimately, the goal is to move beyond virgin plastic, and Coolbrook has also proven the process on pyrolysis oil made from waste plastic, turning it back into new feedstock. Now, Coolbrook aren't just focused on steam cracking, but it is an interesting case study as an industry so ripe for electrification, using vast amounts of energy and, critically, armed with the scale and capital to change. So clearly this campus is absolutely perfectly placed to set up a pilot plant. And over here I can see that this is where the Coolbrook RotoDynamic Reactor is being tested. But it also just looks like a maze of various different pipes and things. Can we go and take a closer look?
Yes, we can. Let's go.
So give us a sense of the scale of potential impact, because we know that these hard-to-abate industries presently don't have many options available to them. But let's say that Coolbrook was rolled out in all of those industries. What's the scope of CO2 emissions saving?
Yeah, it's staggering. It's mind-bending, really. And my reference is aviation with a background from Rolls-Royce. Globally, aviation emits maybe 1.2 billion tonnes of CO2 per year. The heavy industry sector, the total emissions are around 8 or 9 billion tonnes. But with our technology, we can address maybe 2.4 of that. So it's like stopping flying twice.
Oh my goodness. So I'm guessing for a lot of the process, it looks pretty similar to what would traditionally be done in normal cracking. This is the first stage. What's going on here?
Well, this is our feedstock station. So like in the fossil processes, we start with naphtha. Since we are a pilot plant, it's not coming in a pipeline, but we have these containers containing 17 tons of naphtha each, which is for a pilot plant quite a lot.
So we've got our feedstock. What happens next?
The feedstock is pumped into a pipeline, into that direction, and there on top, it's brought to our preheating station, which is on the other side of the plant.
Oh, let's go have a little look.
Yes, let's do that.
So this is the preheating stage, and it is very noisy in here. What precisely is going on?
Well, in order to crack the naphtha, we need to mix it with steam, and we have to make sure that it's all in gas phase. So first of all, the liquid naphtha is coming in via the pipelines and is then evaporated in this evaporator.
Yeah.
Then, as a gas, it is mixed with superheated steam in order to avoid any moisture parts in the blending. And the mixing is done just here on top of me. After it's mixed, you can see there's a combination of the naphtha and the superheated steam. We go to this big knockout drum where we knock out any left moisture. And from there, it is superheated one more time in this superheater, and then it's fed into our reactor. And then we are absolutely sure no droplets are in, because they will demolish our reactor.
So we've come out of the preheating stage, and in here, I think there is one ginormous electric motor.
Exactly. As we have a RotoDynamic technology, we have to rotate it. And we do that with a huge electric engine. Be careful of the noise. It's quite noisy, as you can hear. Woo! This is our engine.
And when we say huge, just how huge are we talking? What in kilowatts?
The engine is 800 kilowatt, rotates at 8,000 RPM. And then we have a gearbox behind it, which speeds up to 24,000 RPM.
God, these are staggering numbers.
This leads to supersonic speed in our reactor.
Now, without wishing to ruin the suspense, unfortunately, we can't open this door to see the reactor with our own eyes. And Patrick will explain why. So we've come just round the corner from the electric motor to another very noisy spot. But this is where the real magic happens.
This is where the magic happens. This is our reactor room, and inside is our RotoDynamic Reactor. It's completely safe into this room, completely inert, so that we can have our reaction going on in full speed and full force.
So we absolutely cannot open that door.
We cannot open that door. Inside, there is only nitrogen to keep the area safe from, for example, any explosion. So we can't breathe inside, there is no oxygen. So we leave it close in order to be safe.
And inside that reactor, that's where the naphtha is being cracked into its sort of constituent components.
Exactly. The reactor is like a big donut shape, and the naphtha steam gas goes in on one side, makes half a rotation and exits, and during that half rotation, the naphtha is cracked into the final products.
So where are we headed next?
So now we go upstairs, so the naphtha is cracked and the final products go completely up to the top of the building, where we do a full analysis of the gases and then go to the end station.
So you can definitely feel the wind up here, but we're right at the top of the chimneys. What's happening here?
Well, here we are at the analysis room of our pilot plant. We want to know exactly what we are producing so that we compare our technology with the existing technology. And that we do in here, inside this little cabinet, where we have our analysis equipment online ready to measure everything that we do.
And I guess that's so that actually you can say to industry, this process is just as good, but it's much more efficient and it's not using fossil fuels.
Well, actually what we want to say and what we can say is that we are better than existing technology. Our product portfolio is up to 10% better than from the existing technology, and that's also the reason why we can make it in this industry.
Which I guess is partly because you can have a little bit more control over those conditions within the reactor when you're doing it electrically versus, say, combustion.
Well, we can steer the time the product is in the reactor and the temperature quite precise. And that gives us the opportunity to steer the output of our reactor.
It's also phenomenal being up here on this, incredibly exciting technology, but looking out and seeing the kind of slightly more archaic petrochemical industry.
Yeah, that's fantastic. I mean, that's where the current technology is running in full capacity, and we want to conquer the world with our technology and deserve a place out there.
Giving them all a glimpse into the future.
Absolutely.
In terms of efficiency, say for example here at this pilot plant, compared completely like to using fossil fuels, how does this compare?
I say it's interesting. So combustion is very efficient by its nature. You get a lot of heat and you can use a lot of that heat. We've got to drive our system through an electric motor and a gearbox, and there's small losses associated with that. So we'd expect maybe 90–95% conversion of electrons into heat that you can use. But the real benefit is that we can integrate our machine in different ways to what you can conventionally do with flame combustion. So we can take hot gas directly into our machine, for example, and heat it. You can't always do that with a combustion system, and you've got residual waste heat. So 90–95% fundamentally in the machine, but we can get maybe 10 or 30% improvement on top of that by interesting ways to integrate the technology into processes.
So it's more efficient, but how does it actually work? This is what's generating the temperature in there. Or rather, this is a scale model of what's going on in there. And what we can see is a cross-section of the RotoDynamic Reactor. It would be the same cross-section also for the RotoDynamic heater. And it is a turbo machine, and turbo machines transfer energy between a rotor and a working fluid like gas or liquid. And typically we see these to generate thrust in, say, a jet engine, or to generate electricity in a gas or steam turbine. And they work because of the relationship between pressure, volume and temperature. PV equals nRT, the ideal gas law. Squeeze a gas and its temperature will increase, let it expand, and it will cool. Physicists have been exploiting this for decades in order to optimize these turbo machines. Now let's take, for example, a jet engine. The idea is to compress a gas, making it ripe for combustion. But along the way, as it passes through stators and rotors in order to do so, it needs to limit temperature increases and limit the amount of entropy or inefficiency that's introduced to that process. Physicists want that process to be as reversible and as adiabatic as possible. Now with Coolbrook, the principle is the same, but the objective is totally different. Here, we want to increase temperature and increase entropy in order to do so. So here's how it works. We have our preheated gas, which passes over these stator blades. An electric motor is spinning our rotor at super high speeds. This accelerates the flow where it hits the diffuser and is going so fast it creates a shockwave. That shockwave has a tremendous amount of energy and has nowhere to go, so it collapses into heat, heating our gas within milliseconds to up to 1700 degrees C. That gas then travels around this sort of toroidal shape and goes through these stator-rotor-stator blades multiple times. It eventually exits here, but it does have the effect of meaning that this is a very dense system, meaning that it's essentially plug and play, replacing what might be a huge furnace with a much smaller system. So very efficient on that front too. To get this into the hands of a real-life customer that they can integrate it into their process, what are some of the big meaty engineering challenges that you're anticipating in order to make that happen?
So part of the issue that we will face as we roll this out is grid infrastructure. So we're talking about big high power machines here, and in the 50 to 100 megawatt region, which is significant. And we're not talking about plugs that you can plug in here, we're talking about real infrastructure challenges. The good news is that, well, there's two things. First of all, that's a problem that's not unique to us. The world is electrifying. High power sources need to enter the grid in order to make that happen, and we can hang on the coattails of that. And second of all, we don't need to go to the 50 or 100 megawatt region from day one. We can start to decarbonise sections of the process with grid capability that exists today and build on that with the customer when that electrification journey rolls out in terms of the grid infrastructure.
Steel, cement, aluminium, chemicals and petrochemicals really are the backbone of our modern society, and so it is absolutely paramount that we find ways to decarbonise them. And that is precisely what we have seen here today. It's something that's super cool, super elegant, and it's just fantastic physics. But that is all that we have time for today. Please do let us know what you think in the comments. Please do like and subscribe. And if you have been, thank you for watching.